Section 1.1, Basic Definitions and Notations. What is a differential equation? Differential equation is an equation which involves derivatives on an unknown function. In other words, the derivative represents the rate of change. So any equation which has any order of differential equation, derivative of the unknown function, is known as differential equation, such as y prime plus y equals x squared, y double prime minus k squared times y is an example of differential equation. K here is constant. This would be the fourth derivative of y with respect to x plus second derivative of y with respect to x equals negative cosine of x. And this is y double prime minus y prime minus 6y is equal to 0. So notice in all these equations, we do have some order of derivative of y with respect to x. Most of the time when you see y prime or y double prime or any order of differential equation, by default, the assumption is the derivative is taken with respect to x, unless they state it otherwise. Meaning, if I have, let's say, y prime of t plus 6y of t is equal to e to the t, so I know when they say y prime of t, I know the derivative is taken with respect to t. In other words, the independent variable is t, the dependent variable is y. Types of differential equations. There are two kinds of differential equations, one of which we'll learn a little bit about it in this course. The other one is a 400 level course, which is required for math majors in applied field. And also it's required for mechanical engineers, which will take in a course called heat transfer, which requires this type of differential equation. ODE is an acronym for ordinary differential equation. And these are the type of equations where what? The unknown function, unknown function is a what? Is a single variable function, such as the examples on top. Notice all of these guys are functions of x. However, if the unknown function is what? Function of multivariables or variable, then the differential equation is called partial differential equation, which the acronym for that is PDE. Whereas for ordinary differential equation, it's ODE. So the difference between these two types of differential equation is the unknown function used in the equation. If it's a single variable, it's ODE. If it is a multivariable, those of you who had multivariable calculus, these are the kind of equations which involve with multivariable functions, such as this guy. This is phi xx plus phi yy minus phi x equals e to the x plus x sine of y. Those of you know phi xx stands for partial derivative of what? Of phi with respect to what? X. So it's not total derivative, it's partial derivative. So something like ut here in this equation, by the way, this is the equation for heat. And the third equation is equation for the wave. Notice all of these equations are PDE type, which they involve multivariable functions. So ut is partial derivative of u with respect to t. Do you see it here? And utt is a partial derivative of second partial derivative of u with respect to t. So in these two cases, the independent variables happens to be t and x, not just x. Do you see it? That's why they're under the category of PDE, not ODE. Alrighty, so these are examples of ODE. So this is like x squared y double prime plus 5xy prime plus 4y equals 0, and so on and so forth. The next thing we like to learn is what do you mean by the order of differential equation and the notation. Order of differential equation is the highest derivative in the equation is called order of differential equation. What does that mean? The highest derivative of derivative in this equation is 2. Do you see it? It's y double prime. So therefore, this is called second order, what? ODE. This guy has y prime in it only, so this is called first order ODE. This guy has this funny notation, which stands for third derivative. And let's talk about that notation. Either we use this notation, which stands for dy dx, or when the derivative, the order of derivative, what, exceeds 2 or 3, then we use what? Superscript with parentheses around the number. So this guy stands for the nth derivative of y with respect to x. So in other words, when we have something like, let's say, y to like exponent, like the superscript, parentheses 3 of x, that just stands for the third derivative of y with respect to x. So that's the kind of notation we use sometimes to eliminate putting so many primes on top of the y. Suppose you have like, let's say, 10th order ODE, you don't want to put like 10 primes on top of y, so you want to use this notation right here, depending what n is. Of course, n is what, greater than or equal to what? 1. All right. So this guy is the third order, is that right? Third order ODE. And this guy is fourth order because that's the highest derivative. Fourth order, what? ODE, which I could have written this as y, what? Fourth order of x plus what? Second order plus cosine of x equals 0. So either of these notations are used interchangeably, so it'd be nice to get used to either form. Either the Leibniz notation, dy dx, or this notation which is used when the order of differential equation exceeds 3, then we use parentheses. Okay, question, the 64 million bucks question is why differential equation? In other words, why do I care? Well, remember, differential equation deals with what? Derivative. And derivative is rate of change, okay, in real life. Whatever changes with respect to some independent variable, you can bet your money the equation which governs that mathematical model has to do with derivative, which is differential equation. Some of the common examples which I came up with are the following. The first one is Newton's second law of motion. So as you know, every time object is subject to a force in order to move from point A to point B. So that object is what? Is subject to a force. In other words, anytime an object is in motion, according to Newton's second law of motion, that object is subject to a force which is proportional to the acceleration. Notice in this case, F is the force applied to the object. M is the mass, which we assume it's constant. And A is the acceleration. Acceleration, do you see it? So a force which is what? Associated with an object in order to put the object in motion is proportional to the acceleration. However, Acceleration is the same as what? Derivative of the velocity with respect to time. There it is. So as you can tell, we have a differential equation because dv dt is the same as what? V prime of t. So that's a differential equation right there. Hooke's law. That's like if you have the spring, right? Okay, here is a natural length of the spring. But let's say due to some force, we like to kind of what? Expand this or stretch it due to, let's say, by attaching a mass m to it. So this amount of a stretch is called x, which is known as amount of a stretch or amount of deflection. Amount of deflection. That's deflection. Remember, deflection can be amount of a stretch or compressed, because you can also what? Push the force upwards and what? Compress this. Do you see it? Right? So the amount which what? The spring has been either elongated or compressed is called amount of deflection. And Hooke's law says what? The force due to the spring is proportional to the what? Amount of deflection. And K is called constant spring, which in real life, it means how stiff or hard the spring is, or the material the spring is made of. Okay, then we have Newton's law of cooling, which says dt dt, capital T lowercase t, minus k times the quantity T minus Tm. T stands for temperature of a body. When I say a body, it could be a body of a human being, or it could be objects. T is the time, K is the constant, proportionality constant, and Tm is temperature of the what? Medium. Medium, that's like temperature, the room temperature, or wherever the experiment has been conducted. So if you were on the beach and you decided to see how fast the temperature of, let's say, something is decreasing, so you gotta take the temperature of the ambient, which is what, of the medium, under consideration, because according to Newton's law of cooling, the rate of change of temperature of a body with respect to time is proportional to the difference between the temperature of the medium or ambient and the temperature of the body. You see it. Once again, you have a differential equation. Finally, we have geometric application, which this application is called the orthogonal trajectory problems. Example of orthogonal trajectory problems happens to be what? The polar coordinates. What is orthogonal trajectory problems? These are the type of problems where if you would graph what? The curves, the first set of curves, excuse me, happens to be perpendicular to the second set of curves at the point of intersection. Let's say you got a bunch of straight lines going through the what? Origin, okay? And let's say you got a bunch of concentric circles. You see it. Notice every time the circles what intersects these lines, at the point of intersection, the tangent lines are perpendicular. So those are called orthogonal trajectory problems. And we may or may not cover this, but I thought it would be nice to mention it. What would be the geometric application of this? And it just turns out that's exactly what we used to see in math Calc 2 under the title of polar coordinates. Also, sometimes when you have the curve and you have the equation of the curve, when you find the derivative, that will give you the slope of the tangent line at any given point. However, the question is, if I give you the slope of the tangent line at any given point, let's say point x, y, any random point on the curve, would you be able to find a what? the equation of the original curve as well. Well, going from y prime to y, that would be what? Solving differential equations. So now let's finish this section with write the differential equation for the following statements. It says the rate of the change of population P of bacteria at time t is proportional to the population at time t. So the rate of change is how fast the population is changing with respect to time. So that's what this portion is. So that portion translates to this mathematical statement or expression, which is derivative. It's proportional, so is equals proportional, the constant of proportionality, to the population itself. So in other words, the rate of change depends on the size of the population. As the population increases, so does the rate of change of the bacteria. Okay, so the next example is the velocity at time t of a particle moving along a straight line is proportional to the fourth power's position x. So the velocity is what? Changing. So that would be dv dt. So that's the rate of change. Is proportional. So you got to have what? K is called constant of what? Proportionality. Constant of proportionality. And based on some conditions, it will be predetermined what K is in real life. And this guy is proportional to the fourth power of X, which happens to be the position. So there it is. That's a differential equation. And it happens to be, both of these guys happens to be first order. Do you see it? So these are called first order ODEs. Why? Because the function depends on only one single independent variable, such as t. Thank you.